Hello everyone. Today we're going to be making the connection between pH and pKa. I'm sure we've all seen this reaction before, either in LibreText or in lecture. The reaction describes the reversible deprotonation of CH3COOH, also known as acetic acid. Acetic acid is the acid you find in vinegar, and it's also common in condiments like ketchup and barbecue sauce. This reaction may seem confusing at first, so I'm here to break it down for you. I'm going to be using whiteboard markers to create a visual. The base of the marker will represent the deprotonated molecule CH3COO-. The black cap represents the proton H+. The base and the black cap attached will represent the protonated molecule CH3COOH. And the red caps will represent the OH-, which are the hydroxide ions. So here again is the protonated molecule CH3COOH. Here is the deprotonated molecule CH3COO-, and then the protons, the H+, is going to be right here. And don't forget about the OH-, the hydroxide ions, which are the red caps. Here's the graph that corresponds to the reaction. The graph describes what happens to the pH of a solution containing acetic acid when small amounts of OH are added. The x-axis represents the amount of OH being added to the solution, and the y-axis reports the pH of the solution. This experiment is going to tell us something important about how acetic acid behaves at different pHs. When looking at the graph, you can see that the experiment starts at a very low pH. As OH is added, starting from 0 to about 3 equivalents of OH, the pH rises quickly. This is because the acetic acid molecule still has the strength to hold on to its H+ ions. So let's see that in action. Here you can see that when the initial OH is added to the solution, it reacts with a free proton and is neutralized, making water. This lowers the free proton concentration and increases the pH. However, when more OH is added and the pH begins to approach the pKa of acetic acid, which is 4.76, the molecule starts to shed its H+ ions. The H+ ions stolen from the acetic acid neutralize the OH and make H2O. Since these H+ ions are soaked up by the hydroxide ion and therefore don't contribute to the free H+ concentration, the pH doesn't change. You can see this behavior reflected here in the graph when the pH starts to plateau from roughly 3 to 7 equivalents of OH. When the pH equals pKa, as seen here, it is known that 50% of the acetic acid molecules in solution are protonated and 50% are deprotonated. As more OH is added, more acetic acid molecules become deprotonated until all of the acetic acid are deprotonated. Once this happens, the H+ bonded to the acetic acid can no longer neutralize the OH. Any additional OH will start raising the pH quickly again, as seen here. This mental picture can help you visualize how to answer questions asking you to determine whether a functional group will be protonated or deprotonated at a certain pH value. For any such question, you can start by assuming the pH equals the pKa. When you do this, you know that the molecule in the problem must be 50% protonated and 50% deprotonated. If the target pH is lower than the pKa of the molecule, then you know that the solution must be more acidic than when pH equals pKa. Conversely, if the target pH is higher than the pKa of the molecule, then you know that the solution must be more basic than when pH equals pKa. To make the solution more acidic, more hydrogen ions must be added. Since their concentration will increase, more protons will be available to protonate negative functional groups. Here you can see the H+ ion being added to the solution and protonating the CH3COO- molecules. This leads to the functional group being mostly protonated in solution, creating more CH3COOH molecules. If instead the problem asks you for the protonation state of a molecule when the pH is greater than the pKa, the solution must be more basic than when pH equals pKa. To make the solution more basic, protons must be removed from the solution. Fewer protons in solution will stimulate the functional groups on the donor molecule to deprotonate. Here you can see that as the solution becomes more basic, The acetic acid tries to restore the protons that are being removed from the solution by deprotonating its functional groups. This leads to the functional groups being mostly deprotonated in solution. I hope this video helped you make the connection between pH and pKa. Thanks for watching.